once. Okay. So we'll go ahead and get started. Good morning, everyone who's joining us on the West Coast. Good afternoon to everyone on the East Coast. My name is Allison Theobold. I am the program chair currently for the statistical computing section of the ASA. And on behalf of all of our mini-symposium organizing committee, I would like to welcome everyone to this year's mini-symposium. We're really excited to have you join us for our amazing lineup of speakers, all of which are going to tell us about some very beautiful and interesting and profound things that you can do with statistical computing. I'm going to go ahead and start off by turning it over to Tim Hesterberg, who is our program chair of the computing section of the ASA, to say a few words about our section.
Thank you, Allison. Let me present. All right, do you see my screen?
Yes.
Great. Well, I want to thank the organizers of the symposium. The statistical computing section is a large section because everybody does computing. If you're doing modern statistics, it's based on computing. And so this section puts on the program at JSM. We put on a nice mixer. We have our newsletter. We give awards, this symposium. The offices are listed here. Want to thank the officers for their work. And then I'll mention two things sort of in particular. Many of you may use Python, R, Python. I'm terribly frustrated by Python. I find it a poor design for data analysis. It uses inaccurate algorithms. The linear regression algorithm uses the normal equations by default, which are terrible for numerical round-off error rather than QR. The stats models doesn't use an intercept by default. So this was not designed by a statistician, and it fails if y is constant, some of the computations. There are a couple of people working to make it better. They've got a grant. If you are interested in talking to them about ways to make it better, maybe even contributing yourself, contact them. If you contact me, I can share this info with you. And then second, I've got a personal project of faster nonlinear optimization. One basic algorithm, which is steepest descent, and this is behind these terribly expensive computations that are used for artificial intelligence now. To do a single iteration, cost is proportional to the number of dimensions, the number of parameters, and it converges linearly, which is kind of slow. I've got a way to accelerate this. Newton's method, on the other hand, is quadratic convergence, but the iteration cost is O of D cubed, which, if you're talking about millions of parameters, like in artificial intelligence, just is not feasible. There is an algorithm, conjugate gradient, which, in theory at least, gives quadratic convergence with an iteration cost of O of D, except that's only in theory because the errors build up. I believe I have a stable version of this. So if you want to try these things, or maybe even interested in joint work, contact me. Thank you. And that's it for me.
Thank you, Tim. And the next person that I wanted to have us share a few words is Ron Wasserstein. Ron is executive director of the ASA, just to situate sort of a bigger picture for people who are not as familiar with the ASA, like what our organization is and what we do. And I'll turn over to Ron.
Thank you, Allison. Tim and I work together a lot. And so Tim, I'm going to take the opposite approach to you, and I'm going to go to ancient statistical computing, because as you were saying this, I was thinking about my first statistical computing experiences were with punched cards on an IBM 360. And if anything like any of that sounds like the good old days to you, you're not really understanding where I'm coming from. It really is a pleasure to welcome you to this mini symposium. This is my second year of doing so. And in that year, I have come to appreciate even more how important these kinds of meetings are, but also how they don't just materialize out of thin air. They involve a lot of work on the part of a lot of people in order to bring you these kinds of opportunities. So I know that you will benefit from your participation today. The American Statistical Association is the largest community of professional statisticians in North America. I'm pretty sure it's the largest one in the world, but we'll leave that go. Our members are largely in North America, but we have membership in over 90 countries. And the fabulous thing about the American Statistical Association gets right back to what I was just saying about this symposium, and that is that basically it runs by committed volunteers. Sure, we have an office, and here in Northern Virginia, we have 32 staff members, and they do a lot, but they can't do nearly what all needs to be done without the tremendous number of volunteers. It's something like 1,500 or more members volunteer annually. So I just want to say, get involved. Get involved in this section or other sections you're in. Get involved in your local chapter. If you're interested more in how to get involved, or how to sort of get involved in the larger aspects of ASA, please just send me a note. So welcome and thanks, and I hope you have a great time today. And Allison, I know you're eager to get rolling with Adrian.
Yeah, thank you, Ron. I do especially want to plug, we here at Cal Poly are an undergrad institution, and so we have been really plugging the student membership for the ASA. I think a lot of students don't think so much about joining the ASA, and it actually is it's a pretty great deal, but it also gets you a lot of access to some cool stuff that you can see through the ASA. So I do want to highlight that for the students who are joining us. Thank you to you both for giving us some introductions. And with that, I'll turn it over to Adrian. We have the amazing pleasure of hearing from Dr. Adrian Raftery. Born in Ireland, Dr. Raftery is the Blumstein-Jordan Professor Emeritus of Statistics and Sociology at the University of Washington, joining us from France. He develops new statistical methods for problems in the social, environmental, and health sciences. As an elected member of the U.S. National Academy of Sciences, he was identified as the world's most cited researcher in mathematics in the decade from 1995 to 2005 by Thomson-ISI. Dr. Raftery has supervised 34 Ph.D. graduates, of whom 21 are currently hold or have held tenure-track university faculty positions. And Dr. Raftery will talk with us today about some interesting aspects of statistical computing, specifically with model selection. And with that, I will go ahead and turn it over to you.
So I think the person who's sharing has to stop sharing.
Oh, I think Tim.
It's Tim, you need to stop sharing so that I can share, I think. Just to stop sharing.
As far as I can tell, I'm not sharing, but obviously
okay, let
I
me
must
try
be.
again. It says someone else is sharing. Okay, you're not sharing.
I just stopped it.
You're not sharing. Okay, great. Thank you. So I need to share.
Wonderful.
Okay, well, thanks very much indeed. So it's thanks very much for the invitation. It's great to be here, and congratulations to everybody who has organized this. I think it's just great, and particularly the watch parties I think is a great idea. So I want to talk about statistical inference with model uncertainty. This is my website here, and this is joint work with Anupreet Porwal at Google, whose smiling face you see right here. And this is supported by the US National Institutes of Health through the Eunice Kennedy Shriver National Institute of Child Health and Human Development, also known as NICHD. So the context in which I'm talking here is that of model uncertainty. And I want to talk about the various statistical tasks where this arises. So I'm going to talk specifically about 5 common statistical tasks that are often addressed using statistical models, although not uniquely. First is parameter estimation. Second, interval estimation for parameters. Third is inference about model parameters, which classically is usually dealt with by significance tests, but not only, as we'll see. Then point prediction of data we haven't observed, and interval prediction of data we haven't observed. And if you look at the scientific literature, basically all these statistical tasks arise quite a lot. Sometimes people say, try to say you shouldn't think about all of these. They say you shouldn't think about inference about model parameters, you should just do interval estimation. Or people say you shouldn't do estimation at all, you should just think about prediction. Usually though, I think when people say things like that, it reflects that the area that they're working in doesn't have much need for some of these tasks. But if you look more broadly at the statistical, at the scientific literature, we see that these are all important. So I'm going to talk about all of these. The model uncertainty is very often present in scientific problems that in some sense involve models. Model uncertainty means that the structure, we don't fully know the structure of the model we're using. And there's not much agreement about how best to choose models and account for model uncertainty. Many different methods for doing that have been proposed. And that's my topic. And here I'm going to focus on variable selection in linear regression. And I'll say why I'm using this test bed in a few moments. But for this problem, there are historical approaches before, say, 30 years ago, certainly pre-1990, there were a number of approaches dominated. The very common one was expert domain knowledge, where it was common in the 1980s, certainly, to hear people, statisticians say you should, ask the subject matter person, ask the user. And of course, it's good advice, always a good thing to do, but it's also incomplete because, for example, as Allison mentioned, I work quite a lot in sociology. Sociology depends on surveys, often high quality, nationally representative surveys, and often there are many, like general social survey, to take one example, there are many variables. There might be 500 variables available. We might know for sure that there are 5 variables should be in there, gender, race, whatever education level. And then we might know that maybe most of them, maybe 450, are not unlikely to be relevant. But then in between these, there might be, say, 40 variables that we think might be relevant, for example, as confounders, control variables, but we're not sure that they are. And that's where statistical approaches come in and are really unavoidable. Another approach that was common was where a lot of people said, well, just include all the variables. And of course, all variables doesn't, it's not necessarily very well defined. In this example of general social survey I gave, does that mean all the 500? Does it mean just the 50 that you kind of think might be relevant? And then it's subjective choice. But more generally, including all the variables typically has poor properties because you introduce a lot of estimation areas. We know very well by now. Stepwise methods were also used, and they turned out to have poor performance. There was a book by Alan Miller in 1990 that kind of blew the whistle on the state of the art in this area. Over the past 30 years, a lot of methods have been developed that go beyond these historical approaches. And these are particularly in 2 buckets that I'll be talking about. Bayesian model averaging methods is one kind of method, and penalized likelihoods the others. And these are data-based statistical methods. They've been developed and become widely used over that period. And there are many such methods. We're going to compare 21 of the most popular methods. And I think, you know, that's a kind of a compromise, but we think we're kind of getting most of the ones that are advocated widely. And one of the issues about Bayesian model averaging and Bayesian approaches in general is that because they involve various aspects that have to be selected by the user, there can be many variants. So we can have many different Bayesian approaches for doing the same thing. And that has raised the issue that people tend to get confused and overwhelmed when there are too many choices. So, you know, shy away from a method where there isn't clear advice about which one to do. So one of the things we want to do is compare Bayesian approaches with you know, the hope of providing some guidance for potential users. And as I said, our test bed is going to be linear regression, which is probably the original statistical method. It was first simple linear regression invented around 1870 by Sir Francis Galton, and then in the 1890s, multiple linear regression by Carl Pearson. And it's probably still the most used multivariate statistical method. Certainly there are millions of regressions run every day, and probably tens, maybe hundreds of millions I could name. I've worked a fair bit in meteorology, and there are probably tens of millions run every day in that discipline alone. And it's a template for many other methods. For example, logistic regression, which refers to binary outcomes. And strangely enough, you'd think binary outcomes are more fundamental than the continuous outcomes that linear regression deals with. But actually, logistic regression, which is the main or the most used method for binary outcomes or at least standard statistical method, was built on linear regression rather than the other way around, which is kind of surprising. We've generalized linear models like Poisson regression, Poisson log linear regression, and others, structural equation models, then various kinds of, you know, hierarchical, multi-level, random effects models, mixed models, and many machine learning methods in some way intellectually descend from linear regression, like tree models, you know, regression tree, but random forests and other things. So probably as a result of this very long history, it has the most methods for model selection and inference under model uncertainty. And I would conjecture that qualitative conclusions from a study like the one I'm going to describe are fairly likely to carry over to other model classes, although further research is needed. So even if you think, well, you know, linear regression is old hat, which, you know, isn't necessarily the case, but if you do think that, these conclusions, I think, may still be useful. The canonical model selection problem in linear regression is variable selection. And this is a big problem because if you have p potential variables and all of them may or may not be in the model, then you have 2 to the p possible models. So in the kind of situation I was talking about where there's 40 variables, the general social survey kind of model situation, where there are 2 to the p, so it's 2 to the 40 possible models, which is about 1 trillion. And then, you know, when you go up with higher dimensional inference, of course, you get into number of models that's on the order of the number of atoms in the universe. So Bayesian model averaging as one of the approaches. So the setting, or one of the classes of approach, the setting is we have uppercase K candidate models, M sub K for small k is 1 up to big K, and each model is equipped with a parameter vector theta k. We have data uppercase D and a quantity of interest Q about which we're interested. And this might be a parameter we want to estimate or make inference about, a future observation that we want to predict, or perhaps the utility of a course of action for making decisions. And Bayesian model averaging inference, it just extends standard Bayesian inference using the law of total probability. So in a sense, it's very simple. It's just the posterior distribution of Q, the quantity of interest given the data, is just the sum over all the models of the posterior distribution of Q given the data and the model times the posterior probability of the model, where the probability of the model K given the data, the posterior probability, is proportional to the probability of the data given model K times the prior probability of the model. And this is the posterior probability of model K. The probability of the data given model K is got by integrating over the parameter space, not optimizing as in standard frequentist inference. So we integrate over the parameter space the probability of the data given theta k and mk, which is the likelihood, probability of theta k given mk, which is the prior, and that is often called the marginal likelihood, sometimes also called the integrated likelihood, the evidence, and there are various other names. Here, P of D given theta k is the usual likelihood given a value of the parameter. P of mk is the model prior. So that's the prior probability that mk is the model conditional on the class of models considered. And then probability of theta k given mk is the prior distribution of the parameter under the model mk. For BMA, Zellner's G prior is very commonly used, and a lot of the methods I'll be talking about use Zellner's G prior, which goes back to Arnold Zellner in 1980. And this basically says the prior distribution of the regression vector beta given a model gamma, which is a p-dimensional binary vector that basically says which of the parameters are in the model, which of the predictors are in the model. Given, and this is given the intercept alpha, the residual variance sigma squared, and then G, which is a user-specified prior precision parameter. It's normal with a zero mean, and it's G times the variance of beta hat, which we saw in Tim's slide a few minutes ago. And then here we have the prior distribution of the intercept, and the residual standard deviation is just a standard vague flat prior. And so under this prior, the prior variance is proportional to G over N, and the prior sample size is equal to N divided by G. So it's a nice interpretation. When G equals N, we have a prior sample size 1, and this can be thought of as a unit information prior, which is similar to the very well-known Bayesian information criterion, or BIC. When G equals 1, we have a prior sample size of N. And there's actually a kind of study design argument for using this, which I could discuss with you if you want later. But this is similar to, gives results similar to AIC. And in between, there's G equals square root of N. So that corresponds to a prior sample size of square root of N. And this was proposed by Fernandez, Steele, and others in 2001, but not actually recommended by them at the time. It was subsequently found to perform very well in high-dimensional situations with high-dimensional biological throughput data by Young et al. In 2014. So what's good and bad? What's the good, the bad, and the ugly of BMA? Well, there's a lot of good things. It's the natural Bayesian solution, as I mentioned, so it inherits a lot of good properties of Bayesian inference. For example, BMA point estimators and predictions minimize mean squared error. Estimation and prediction intervals are calibrated, and predictive distributions are optimal in the logarithmic score sense for scoring predictive distributions. And this is on average over the prior distribution. So this is, if you think of it as a sampling, you're sampling from the prior and then sampling from the model given sampled parameter values. And this is something we often think of the prior distribution as corresponding to our prior, expert subjective knowledge. But this is something a bit different, actually, a different meaning of the prior distribution, which is the distribution over which we'd like to have good performance. So it's, you know, in our work. So it's a kind of distribution of the kinds of situations we encounter in our, you know, I suppose in our work. And Jeffries in 1939 first discussed this concept and called it the world distribution, a different concept. I called it the practical distribution. Nilanjan Chatterjee and his colleagues in Park et al. Called it the effect size distribution. Jim Berger referred to it a few years ago, referred to analyses using this notion as empirical frequentist analyses. So what's bad about it? Well, it requires a lot of choices on the part of the user. It requires a choice of the parameter prior, of the prior over the model space, and also because typically the number of models is huge, so big that we can't actually enumerate them, it requires computational approximations. And each combination of these choices leads to a different method. So there are many competing methods, and as a result, users can be confused and overwhelmed and not sure which one to use. And sometimes, depending on the quality of the approximations, it can be slow. So the other kind of side of things with a more frequentist flavor is penalized likelihood methods, which convert variable selection into optimization. So here, if we kind of, you know, hide this for a minute, this is just the ordinary least squares estimator. This is the residual sum of squares, but penalized likelihood adds a penalty to that. And the canonical method is the lasso, proposed by Tibshirani, of course, in 1996. And the penalty here is a penalty parameter lambda times the sum of the absolute values of the parameters. And it turns out by a kind of miraculous result that this leads to a sparse estimate. So you're doing estimation and quite a few of the parameters get estimated to be zero. So what's good about this? Well, it's computationally efficient because it leads to convex optimization, and, you know, gradient descent methods have been used. And Tim was also mentioning this conjugate gradient descent, which gives, you know, quadratic convergence. But Tim sounded some useful cautions. Users, there's a smaller number of choices than for Bayesian methods, than for BMA. Users essentially know which methods to use because there's an argument from authority to the GLM net package. And then there's the oracle property, which says that true predictors are included asymptotically in the select model. What's less good is that actually the oracle property sounds great, but the converse doesn't hold. So false predictors can belong asymptotically to the selected model. So it actually does not do consistent model selection, unlike typical Bayesian methods. Thus, it often selects large models and can have many false positives and can overshrink true signals, and it tends to be unstable when there's high correlation between predictors. And there's no at least standard uncertainty quantification. But the result of these good and bad of these two classes of methods is that penalized methods have been become more popular than Bayesian methods, even though their statistical properties are less good for some tasks. And I suspect that that's due to the combination of their reputation for computational efficiency and also the fact that there are fewer choices. So our users are less overwhelmed. So the most cited penalized likelihood paper is cited about twice as much as the most cited BMA paper. So we wanted to see among all these methods, basically to compare them and try and give some guidance because it's a kind of confusing world of model uncertainty and model selection out there. We used simulation studies, and we carried out 14 simulation studies, each of which is based on a real data set. Now, this choice is not very common in statistics. In statistics, there's a tendency to do simulation studies, but to basically for the user, or sorry, for the writer, the researcher, to design their own simulation study and to pick their own parameter values and so on without direct reference to data sets. And I think that leads to some lack of potential credibility. It's kind of this remarkable fact that almost every paper I've seen in the statistics literature that proposes a method does a simulation study where their method comes out on top. And partly, well, given that the authors have selected and designed the simulation study without necessarily reference to data, it obviously raises some questions. And we wanted to avoid that situation and do simulation studies based on real data sets, which incidentally is much more similar to what computer scientists typically do when comparing methods. So when you're doing a simulation study based on real data, that's pretty easy to do for prediction. So if you're trying to predict out of sample data, basically you do some kind of cross-validation. You divide the data into a training set and a test set. You fit your model or apply your method to the training set, use it to predict the test set and see how things do. Of course, there are various ways of choosing cross-validation and so on, but that's straightforward. For inference, like parameter estimation, interval estimation, inference, that's a lot harder because we don't know the truth, right, for a real data set. And that's why, I think that's one of the main reasons why statisticians tend to design their own simulation studies, because then they do know the truth. So our approach is to develop a generating model that represents the data set well. How did we get that? Well, among all the models, we choose the largest model, the one with the most predictors, for which all the predictors are significant at a conventional level. We chose the 5% level because that's probably the most used in practice. And then we simulate data sets from that from that model using the parametric bootstrap. And the resulting data sets have the same design matrix as the original data set, and they've the same typically non-normal error distribution as the data, and they vary only in the response vector. So we're as close, I think, as we can be to the data set while still knowing what the underlying truth is. The data sets, we filtered the entire University of California Irvine database, and we found that there were only 6 data sets in there that were we could find that were appropriate for our purposes. And we added to that some high-dimensional data sets from the R omics package, chemometrics data, and 4 classical data sets that are often used for analyzing regression. And so these 14 data sets, they include tall data sets of the standard with a lot more observations than variables, wide data sets, kind of the opposite, and then borderline data sets where the number of variables and observations are comparable. And here we see on the x-axis we've got p, the number of variables. On the y-axis we've got n, and you can see we have these wide data sets over here, kind of classical tall data sets here, and then kind of borderline in the middle there. So the metrics we use to assess performance for point estimation, it's root mean squared error. Okay, pretty standard. For interval estimation, we use the mean interval score, which is fairly recent. Tilman Gneiting and I proposed it, 2007, so not so recent, but it seems to have become maybe the reference method for assessing interval estimates. For inference, we're comparing basically methods that just give inclusion or not inclusion, and also Bayesian methods that give posterior probabilities of inclusion. And so we use the area under the precision recall curve for the resulting curve, which can assess both of these. And this avoids choosing a single threshold for posterior inclusion probabilities and allows us to assess the posterior probabilities as a whole. Then for prediction, okay, we just use the R squared in the test data set. Interesting wrinkle is this can be, in theory, it can be negative because if the mean in the training data set is a bad prediction of the test data set, then you can actually get negative test R squared. And interval prediction, we use the mean interval score for predictive intervals. Number of variables, CPU time, and we normalized all the metrics by the value for BMA with the Jeffreys, Zellner, Xiao prior, which is maybe the oldest method here. It goes back to 1980 and actually still performed pretty well. But basically this is to normalize, so we have, it doesn't really matter which which method is used for normalization, because this is just to be able to compare across data sets and metrics. So, and then the score is the average of all 5 methods, but some of the methods don't measure intervals, like the lasso, for example, and so we there use the partial score, which is the average of the 3 metrics, not 5, that don't measure the intervals. So the methods that we compared here are the 21. So BMA information criterion based, there's one which uses the BIC and the BMA package, another one that uses BIC and the BAS. This is Bayesian adaptive sampling, which is a package, a great package developed by Marlies Clyde. AIC, using AIC weights, this has been very popular in ecology. Then the Zellner's G prior that I've talked about. So there's the old Zellner and Xiao, which uses actually a kind of Cauchy kind of priors. The G equals N unit information prior, the G equals square root of N, G equals 1, very like AIC. And this is a prior that was recommended by Fernandez et al. And then empirical Bayes, where G is selected based on the data. There's a global version where there's just one value and a local version where there's one different value for each model. And then hyper G, where G itself is treated in a Bayesian way. Other Bayesian approaches, the spike and slab method, the horseshoe method, the non-local prior method, an EM variable selection method, spike and slab lasso, and then the penalized likelihood methods, the lasso itself, of course, the SCAD method, the elastic net, and the MCP method. So these are, well, there's 20, and then yeah, that's, sorry, that is, I think, 21. So results, here are the results. And what you see up here, basically, we've got along the top, we've got so along the side here, we have these methods that are listed, these 21 methods. This is their rank. And here's the overall score that I mentioned. And this is the partial score, which of course is available for all of them. Jeffrey Zellner Xiao is here, and everything is normalized so that this is 1 for these, for that method. And green is better than the reference method. Yellow is pretty close to the reference method, and then orange is substantially worse. And typically there was a kind of a big gap, so to define the orange. And if we look, there are 3 methods here which are adaptive BMA methods, and they did best. Then we've got a bunch of other Bayesian methods here that round out the top 9. Then we've lasso in here that comes in the middle, lasso and SCAD, and then a bunch of other methods round out the end. So there's just a few things here. So first thing is the results are actually similar across all 5 statistical tasks, which surprised me a lot. I was thinking it'd be different for different tasks, although there's one exception to that that I may point out. Bayesian methods were better than penalized likelihood methods overall. 3 adaptive BMA G prior methods did best. So the G equals square root of N came out on top, and this is a kind of a compromise between AIC and BIC in a way, although it's not designed that way. The hyper G and the EB local empirical Bayes. AIC weights did very badly, and that's kind of given their prevalence in, especially in ecological disciplines, that's a kind of important fact. And then the BIC based and lasso were best in class at the time they were proposed in the mid-1990s, but the BIC based has been overtaken on the Bayesian side of the house, if you like. The lasso is still did better than the other penalized likelihood. One thing is the BAS package uses a very large number of MCMC iterations by default. And we found that it did just fine with just a standard 10,000 iterations. And then computationally, the BMA was competitive, about the same as lasso, particularly with these, the G equals square root of N and the empirical Bayes approach. So some quick comments here. There have been other comparisons between variable selection methods, but actually, including one that I was involved with myself, they're not using empirically based, they're using non-empirically based simulations of the kind that I've been criticizing. So mea culpa myself, a narrower range of methods considered, and only a subset of statistical tasks considered. So sometimes they just considered point prediction. So I'll just say the three best methods satisfy model selection consistency, and are not subject to the Bartlett paradox. This is, and just an interesting comment is that the G equals square root of n method that came out on top is actually similar to BIC, but with the logarithm of n complexity parameter in BIC halved, divided by 2. So I'm going to actually skip over this for the want of time. Just one other issue is model space priors. So how should the prior over model space be specified? And most model space priors are based on the so-called Bernoulli prior, which basically says that the probability, so it's governed by a parameter phi, which is the probability of inclusion of any given parameter, and the probability of a model is the probability of phi if the variable is in the model, or 1 minus phi if it's not, just the product. So these are treated conditionally independently given phi. The uniform prior is uniform across all models, and that corresponds to phi equals a half. Beta binomial prior allows phi to be estimated, so it puts a prior distribution on it, which is itself uniform, or beta 1, 1. And there's a third prior that was proposed by Castillo et al. 2015, which looks like this. It's the probability of m gamma is proportional to p, the number of parameters, to the minus kappa times the number of parameters. And it's constrained to be less than the number of variables in the the maximum of n and the minimum of n and p. And this is proposed by Castillo et al. In the Annals of Statistics in 2015. And they claimed to prove that this was the best approach. So the best model selection approach. So we kind of wanted to test that empirically. And we took the G equals square root of n parameter prior, and we looked at these 4 parameters. So the best was beta binomial. The second best was uniform, and then the complexity priors actually were quite bad. So I'm not sure what the proof in this paper actually does, but there's something to look at more closely in there. So one other question that might arise is model averaging better than model selection? Right, so is there any point in model averaging? And we did comparison of Bayesian model averaging and Bayesian model selection for the 3 top BMA methods. And so here are the numerical results. And actually, there's a rather surprising result, which is that Bayesian model averaging was much better than Bayesian model selection. I mean, it's not even close. So and so the answer to that question is a resounding yes. And I was a bit surprised by that because, again, I thought there would be some improvement, but not as dramatic. So to kind of summarize here, we've compared 21 model selection methods and model averaging methods via database simulation studies for 5 important statistical tasks. 3 adaptive BMA methods perform best. The Bayesian model averaging with Zellner's G prior and G equals square root of n, the hyper G prior, where there's a Bayesian prior put on G, and the empirical Bayes, where it's estimated for each model separately. And also the G equals square root of n and the empirical Bayes local were computationally efficient with the BAS package, as long as you just do, limited the number of iterations to 10,000, for example, and which is all that's needed. So I would kind of suggest in academia, there's a bit of an incentive to doing new stuff and, inventing new methods. But here, I think it might be some advantage to also focus efforts on communicating and perhaps building on these methods that have been shown here to be best rather than developing completely new ones. The beta binomial model space prior outperformed others. Model averaging turned out to be better than model selection. And of course, further research is needed. Extending it to other model classes like generalized linear models, including the choice of link function and the mean variance relationship. Similar comparisons for hierarchical models, mixed models, and so on. Structural equation models I mentioned, other model classes, various machine learning kind of problems, maybe deep learning, AI. And I would conjecture that broadly similar results hold in other settings. I think that's certainly a good conjecture to kind of investigate. So here are some references: a PNAS paper in New England Journal of Statistics and Data Science, and data and code are available here. So that's it from me. So thanks very much. And if there's time for questions, which I think there should be, I'm more than happy to take them. I'm just going to.
Adrian, thank you. That was terrific. So I think mechanically, if you would like to ask a question as an attendee, there's a Q&A option at the bottom to type in. So I believe that's the case. We have a few minutes here.
Yeah, I don't know if it's possible for people to speak, but
I don't think we've put that option in.
yeah, okay.
Yeah, if not, I have a really quick question. Dr. Raftery, that's a great talk, very comprehensive. And there is a table, it's like a heat map where you're comparing the different method.
Yes.
I saw in the computing time, oh, that's kind of very large range. Some
Very
are,
large.
yeah, some are fairly quick, it's 0.9. Some are 254. I was wondering, and first, what's the unit for the CPU time? Is that second or minutes or hours? And second, like, could you give some insight about this time? Why, like, for example, the NLP method taking that so long?
Yeah, that's a really great question. And of course, this is basically what we did to really, one of the difficulties about a comparison like this is that, you know, if a method doesn't do so well, you know, the authors of the method can come back and say, oh, you did it wrong, or you didn't use the right one. So we tried to use the default, you know, methods that they had provided themselves in software, and we restricted ourselves to methods for which there was, you know, publicly available kind of stable software. So we just ran whatever the authors, you know, had provided, often in R packages, typically in R packages. And the reality is, I think some of this is due to, you know, slow coding. I mean, just poor coding, and that you could probably, the NLP, my guess is you could go in and probably gain, you know, an order of magnitude, maybe even 2 orders of magnitude by just, you know, dealing with improving coding efficiency, which was done by the authors, because often this is, you know, it's publicly available, but it's research code in quite a few cases. So that's I think that's the answer. I think the ones where, you know, with the BAS package, or indeed the BMA package I was involved with, and the GLMNet, which implements Lasso, they're, you know, computationally, there's been a lot of effort to make them efficient. So so these are probably, you know, these probably do reflect the computational intensity of these particular methods. But I think others like NLP, yeah, I would say that somebody could, you know, if somebody knowledgeable got dug into the code, they could improve it, you know, dramatically, pretty quick.
That's a great comment, especially for the NLP, I think. Yep. Thank you.
Thanks, Adrian. At the moment, I don't see any questions in the chat. If I could, I wanted to ask one more, I think, quick question on the same slide. Is I noticed AIC down at the bottom tends to have some of the more red performance, and the reason I mention it is in a lot of classical statistical introductions to this problem, the AIC is often referenced, and I'm just curious if you can share a couple words on why you might see this performance with AIC in particular.
Yeah, and it's, I mean, so this is for inference with AIC weights. And I think it may be that AIC is, it's not a consistent method, and it tends to select big models. And that can be okay for, if you're focusing purely on prediction, although it doesn't do well in prediction either, really. There's a kind of a theory, but it may in real life, if you like, because here this is a simulation where in some sense what we're simulating does not correspond to the model that we're evaluating, right? Because the model that we're evaluating, it involves a design matrix that it involves error terms that are not normal. It involves design matrices that have all kinds of quirky features and so on, which are in the data. So it could be that with AIC you just get very large numbers of models, many of which are not very good, and you're kind of into the averaging goes a lot of models that are not that are not great. But that is something to really give a definitive answer to that, I think would require more research. But I think it's something we've learned. I mean, AIC goes back to the it goes back over 40 years and maybe 50 years. And we have learned about the value of parsimony, especially in more high dimensional settings, and I think the methods, the Bayesian methods, and indeed to some extent Lasso they're more parsimonious, and the Bayesian methods they're quite parsimonious when it's appropriate.
Terrific. Thank you so much. I think at this point, for the sake of trying to stay with the program, I'd like to move to the data jamboree. But Adrian, on behalf of the organizers and attendees, I want to thank you again. This was a wonderful talk. I think a great framing for this conference. So thank you again.
Well, thanks so much. It's been great to be here.